Hello, welcome back to Codex. Today's speaker is Professor Daniel Freeman. Professor Freeman received his PhD from Texas A&M under the direction of Thomas Schlemprecht. After a postdoc at UT Austin, he began his current position at St. Louis University in 2012. Dan is an expert in the geometry of Banach spaces, and he frequently applies this expertise to problems in frame theory. Today's talk is no exception, as Dan will tell us about discretizing LP norms with an application to phase retrieval. Take it away, Dan.
So thank you, John, for the introduction, and thanks a lot for allowing me to speak in this seminar. I think it's pretty fun that we're still able to have seminars, even though we can't meet in person. And what's particularly fun about speaking today is my parents get to listen to me give a talk. So that's it's exciting. Hopefully they're here. Okay, so actually, maybe I should start off. So this is joint work with Dorsa Ghoreishi. And the outline of my talk is first I'm going to give an outline and introduction to the problem. And then I'm going to discuss the connection with the problem with frame theory. And so it's going to be a problem in geometry of Banach spaces that is very closely related to frame theory, and we're going to discuss some of those connections. And so the idea about the problem is going to be discretizing norms on subspaces of Banach spaces. We're first going to look at the case of the Hilbert space, and then we're going to see how does this going to change when instead of looking at L2, we look at some LP. You can consider the problem for any P. We're specifically going to look at this case because that's where we proved all of our results. So that's what we'll focus on. And then afterwards, I'm going to show how these Banach space ideas can actually be used to give applications for stable phase retrieval for frames of Hilbert spaces. So we'll discuss what is phase retrieval and how does that relate to discretizing different Banach space norms. Okay, so let's first think about and introduce the problem. So we can consider any P and look at a subspace of capital LP. This R can be any measure space. We're just thinking about R as an example. And so if you have a subspace, then that means the norm is given exactly by this integral. And what we want to know is that when can we replace this integral with a sum? So instead of integrating over the entire real line, when can you choose sampling points in the real line so that integrating over the whole real line is equivalent to just summing over those sampling points? And so this is something that comes up a lot in applications that I'll talk about later. One clear necessary condition for this is there has to be a boundedness condition on the infinity norm. And so the idea is that once you sample, if you look at any of these particular sampled values, if a particular value is much bigger than the LP norm, then this upper bound would be impossible. And so the idea is that there has to be some bound on the infinity norm of every function. Otherwise, just doing this point evaluation would be too big. And so there's a clear necessary condition for if you want to discretize this integral, then the infinity norm has to be bounded by a multiple of the P norm. here's one clear necessary condition, and I don't think there are any other obvious necessary conditions. And so this is the condition that we're going to focus on. And now we're going to change the problem a little bit. So before we were looking at LP of R, now we're looking at LP of a probability space, and we're going to think about how does this problem change. And so now, instead of integrating for all of R, you just integrate from 0 to 1. And the law of large numbers gives us that you're always able to sample points so that the sample average is proportional to the integral.
Hey, Dan, quick question.
Yeah.
The sample average you just circled, that DT is a typo, right? It doesn't belong in the sum.
You're absolutely right. Thank you. Okay, so
Thanks.
that should be, that was a cut and paste error. Okay, so law of large numbers gives us that no matter what dimension your space is, if you pick M big enough, if you look at the sample average, it's going to be very good approximation to the integral. So now the big question is, how big do you have to pick this M? So we know that there exists some M where if we sample by M points and look at the sample average, it's really good. But how big must M be? In particular, big question is, when can the number of sampling points be proportional to the dimension? So we get another necessary condition here, that if your sampling points is going to be proportional to the dimension, then you have to have another bound on the sup norm. And so the idea is that if your infinity norm is not bounded by this, then doing this, you can't look at the sample average and be bounded here, is the idea. And so in both cases, there's a clear necessary condition that if you want to do discretizing of an integral norm, you have to have a bound on the infinity norm. And this is all.
I'm sorry, can I ask you a stupid question?
Oh, no problem, sure.
You say that, but you haven't heard the stupid question.
Okay.
So you said I need the infinity norm to be small, but it seems like I just need to be small on the particular points that I chose.
Yeah, okay. So I definitely skipped over a little thing. So that's a great question, actually. So I put here after a possible change in measure. And so the idea is that this can be thought of as doing a change in measure where each of my sampling points has measure 1 over m.
Yes.
And so once I do a change of measure to get, and so now my measure space is 1 over m at each of the sampling points and 0 everywhere else, then in LP of this measure, I have exactly this bound. This bound here is exactly this bound here.
I see. Okay, thank you very much.
Yeah, so that's actually a great question, Joey. So yeah, so another good thing to point out is that once you do the sampling, the measure goes away. And so doing a change in measure does not affect your sampling at all. And so it's fine to do changes in measure because it won't affect whether or not you can be sampled. Okay, so both of these problems have a nice necessary condition on the infinity bound. And let's talk about compare and contrast between them. So one difference is that if I allow M to be an arbitrary measure space, I can look at infinite dimensional spaces. And I can think about discretizing the LP norm for infinite dimensional subspaces of LP. And that one's pretty obvious, but there's actually, interesting enough, the necessary condition on the probability measure restricts what finite dimensional subspaces you can look at as well. And so, can you guys see me?
I can see you, but I can also see that iPhone or iPad is.
Okay.
skipping.
Okay.
Oh,
Yeah,
here we go.
we're back. Okay. So by allowing M to be an arbitrary measure space, we can consider the problem for more subspaces. But if we look at specifically M as a probability space, this gives us a ton of really great tools. So a lot of the best techniques in sampling theory are probabilistic techniques, things where you don't know exactly which points you want to pick to sample, but if you sample randomly, then with high probability, something good happens. And so by considering probability spaces, we have lots of really great techniques. And also a nice thing about looking at probability spaces is that discretizing is always possible. And the only question is, how many points do you need to use? So for this talk, I'm going to mostly be focusing on this probability space one. And okay. So, oh no. Okay, good. My slides are working. So what's the connection to frame theory? So we'll take a Hilbert space H, and then we say a collection of vectors is a frame if the sum of the squares of the frame coefficients is proportional to the norm of a vector. And likewise, we'll say a collection of vectors is a continuous frame if the norm of every vector is proportional to the integral of the frame coefficients. And then now if you have a frame or a continuous frame, you can look at the analysis operator, and that maps a vector to the collection of frame coefficients. And being a continuous frame is equivalent to the frame operator is an embedding of your Hilbert space into capital L2. And so that's the key idea that we're going to use, is that being a continuous frame means we have a nice embedding into L2. So if we relate this to, looks like there's some lag with my slides. Okay. I'm gonna try sharing in a different way because this is not working. Okay, so I just plugged in my iPad and the screen doesn't look as cool, but hopefully there's not going to be any lag. Okay, so what's the idea? We have a continuous frame, and it has a particular analysis operator. And so the range of the analysis operator is a closed subspace of L2. And so now discretizing the L2 norm on this subspace is equivalent to sampling your continuous frame to get a frame of H. And this is something that gets done a ton in frame theory. So this is my giant list of papers and examples that I like that involve sampling continuous frames. So the very first paper here is the most cited paper in frame theory, which really popularized frame theory. And all of the frames created in this paper are done by sampling different continuous frames. And so frame theory really started out with creating frames by sampling continuous frames. They weren't called continuous frames then, but they were done by sampling coherent states, which are specific types of continuous frames. So another really important result has to do with random sampling continuous frames. And so they proved that if you have any continuous frame over a probability space and your Hilbert space is n-dimensional, then you can get a nice frame for it by sampling using n log n number of points. And so so this result says that every continuous frame for an n-dimensional Hilbert space, if you sample uniformly, then with high probability, you get a very nice frame of n log n number of vectors. The next reference, this is a textbook that used, gave a lot of nice applications of continuous frames for math physics, and they asked some really interesting questions about continuous frames. This paper used the co-orbit theory of Feistinger and Gröckenig to prove some nice results about sampling continuous frames. This one's a huge paper. They solved the long outstanding Cadison-Singer problem. And Nitsan, Alevsky, and Ulanovsky proved that their solution to the Cadison-Singer problem can be used for constructing frames by sampling continuous frames. And they used this result to prove that if M is any finite measure space in R, then L2 of that has a frame of exponentials. These papers considered frames of exponentials for fractal measures like the Cantor set. This one has to do with if you have some operator on a Hilbert space and you look at iterated powers of that operator, when can you sample that to get a nice frame? Here, this paper, Hartmut-Fuhrer talked about constructing frames of translates for L2 of a group. And lastly, these papers are about random sampling continuous frames to obtain frames which do stable phase retrieval. On this last one, so this is the code seminar, and so here I guess I should make a reference to that. This has to do with sampling P designs and obtaining stable phase retrieval for that. So there's my codes reference for the codec seminar. Okay, so there's tons of great examples here. And all of these are like, you want a frame plus some nice properties. And using continuous frames and sampling them is a useful technique to help in that. So one of the big questions was posed in their physics textbook: when can you sample a continuous frame to obtain a discrete frame? And so with Darren, we proved that we solved this problem, proved that every bounded continuous frame may be sampled to obtain a frame with H. And so this proof used that same solution to the Cadison-Singer problem that Nitsan, Alevsky, and Ulanovsky first used. And another fun thing about that is that the Cadison-Singer problem cannot be used to prove this theorem, but the solution to the Cadison-Singer problem proves something much, much stronger, and that stronger results can be used to solve this. Okay, so how does this relate to discretizing norms on subspaces? Well, if you consider a subspace of L2 of some measure space, which satisfies our necessary boundedness condition. Well, this being satisfied means that X is the range of the analysis operator of a continuous frame. And so then by using the above theorem, we can sample our continuous frame and discretize it. And so if you have L2 of any measure, you can discretize that on a subspace as long as it satisfies this necessary boundedness condition. Okay. And Limonova and Temlyakov proved that this also works for probability measure spaces, that if you have a subspace of L2 of a probability space, which satisfies this necessary boundedness condition, then you can sample with a number of points proportional to the dimension in order to discretize the L2 norm on that subspace. And so what this says is that in the Hilbert space case L2, both of those discretization problems are completely solved. So what happens for P not equal to 2? One thing you might ask is, well, both of these results rely on the solution of the Kaston-Singer problem. Can you extend that? I don't think so. The solution to the Kaston-Singer problem is very much uses Hilbert space techniques, and I don't see any way that can be applied for LP for P other than 2. So we lost a giant tool if we look at LP for P not equal to 2. And so there's a lot of papers on this, and I've collected some of the results here. So we have a probability space. We pick some P and look at an n-dimensional subspace of LP. Oh, and I think I switched from capital N to lowercase n. So this is capital N is our dimension. And we assume that we have a certain entropy bound. So I'm not going to define exactly what it is because it's pretty technical. But the idea is you want to cover the unit ball of xn with different L infinity balls of certain size. And now if you want to cover the unit ball of xn with a single L infinity ball, then that gives you this necessary bound on the infinity norm. And so the idea is that there's a certain condition that's pretty technical, but it includes the necessary boundedness condition. And then they proved that you can pick m on the order of the dimension times log of the dimension squared number of sampling points in order to nicely discretize the LP norm. And so for P other than 2, assuming this entropy condition, you can discretize with n log of n squared points. And it's clear that you need at least the dimension number of points, but it's not clear, is this log of n squared, is this necessary here, or is it an artifact of the proof? And so that was an open question. Okay. So what we proved is that there's a uniform constant so that for any P strictly less than 2, we can construct a subspace which satisfies the necessary bound, but you can't pick m on the order of the dimension sampling points in order to discretize it. And so what this is saying is that for P less than 2, you cannot discretize the LP norm on subspaces using a number of sampling points proportional to the dimension. And I think for p equals 1, we get m has to be bigger than the dimension times log of n to the 1/2. And so there's some room between a non-trivial lower bound that we get and the upper bound of log of n squared. For p other than 1, I haven't calculated exactly what the lower bound is, but we do know that there is a lower bound. Okay. So this is kind of cool because it says in the Hilbert space case, you can discretize perfectly, but in the Banach space case for p less than 2, you can't. And so, you know, this theorem, having this extra factor here, something like that is necessary. So that's pretty cool. Okay, let's talk about the idea for the proof of this. And we're going to first consider the case p equals 1, because that one's a little bit different than the other p. Okay, so we're going to construct a subspace of capital L1, which you can't discretize well. The key property that we're going to use is that if you have a sequence of vectors, which is equivalent to the unit vector basis of L1, so if you have a sequence of vectors where the norm is exactly of linear combinations is exactly the sum of the coefficients, then you can perturb it by vectors uniformly bounded in norm. So if you start with some xj and then pick any vectors yj whose norm is less than 1/2, then if you perturb your xj by these yj's and look at norms of linear combinations of this, it's still proportional to the sum of the coefficients. And so this is something that is completely unique to L1, that you can perturb vectors by vectors whose norm is bounded by 1/2. And so we're going to use this. Okay. So we're going to construct a subspace of capital L1, and we're going to do this where you can't discretize it nicely. And so we first pick any natural number n, and then our dimension of our subspace is going to be this. And so the dimension of our subspace is going to be little n plus 2 to the n, 2n to the n. Okay, so now I'm going to draw some fun pictures on how we do this. Okay, so I'm going to take the interval 0 to 1, and I'm going to divide it into capital N pieces. And then now I'm going to build a basis by on the first, we're going to look at the first little n pieces. And on each of these pieces, I look at a vector that has height n, capital N, and width 1 over n. And so x1 is going to be n times the indicator function of this. X little n is n times the indicator function of n minus 1 over n to n over n. Okay, so this is this is the graph of my first vector. Okay, so I have a bunch of vectors that all they are really simple, just unit vectors of width 1 over capital N and height capital N. And then now I'm going to make more vectors. And for each of these additional vectors that I'm going to make, I'm going to divide each of these small intervals into 2n pieces. And so I have little n intervals of width 1 over n. And then now here I have each of the above intervals is divided into 2n subintervals. Okay. And then now what I'm going to do is make a vector that on this part out here, it is height capital N. And then on each of the teeny subintervals here, I'm going to have height N on one of them. Okay. So that is for n less than j less than capital N, my vector is going to be, it's going to be something like this. And then this will be indicator function of j minus 1 over capital N to j over capital N. Okay, so I have two types of vectors that are going to be in my basis. So the first type is just indicator function of a tiny interval here. And then the second type is going to be indicator function of an interval out here, plus these teeny slivers. And so for each of these intervals here, I divide it into 2n pieces. And for each of these subintervals, I add on an indicator at that to this vector here. Okay. So if I didn't have this piece right here, I would just have a bunch of disjoint vectors that is isometric to L1n. But by adding these overlaps to the first part, I'm going to mess things up when I sample. And so let's think about what's going to happen if I try to discretize the norm on the span of these xj's. So the span of the xj's or the L1 norm on the span of these xj's cannot be discretized nicely. Be discretized using m on the order of n points. Okay, why is that the case? Is because if I sampled the interval 0 to 1, for each of these intervals here, I have to pick at least one point, because this vector is only supported on this interval. And so if I want to discretize the norm on the subspace, I have to pick something in here. But if I look at a vector of this form, I look at my sampling points for each of these subintervals. I've picked something. I then pick a vector of this form, which is 1 on all of those sampling points that I picked. So when I try to discretize the norm of this vector, I'm going to get something that's much too big, because I should only be this vector should only be affected by one sampling point, because it's norm 1, or some constant number of sampling points, but it's getting hit at least little n times. And so if I try to discretize the norm on this subspace, I've oversampled this vector little n number of times. And so little n is how much I've oversampled, which relative to the whole dimension is more than log of this whole dimension to the 1/2. Okay, so this is why you can't discretize the norm on this subspace. Okay, so hopefully that picture was fun, because I like drawing pictures. So one thing though is that this will only work for L1, because if I tried to do the same thing for LP, doing this perturbation of the vectors totally changes the subspace, and so it's not gonna work. So, well, if I look at different subspaces of LP, I have to have a different technique. So let's talk about that. Actually, how about let's not talk about that? Sorry. I'm running a little low on time. So let's talk about now the connection between this idea of discretizing LP norms and applications to phase retrieval. So we'll start with a continuous frame with a particular analysis operator. And the nice thing about a continuous frame is that you can linearly reconstruct every vector in the space from the frame coefficients. So if I know what the frame coefficients are, I can reconstruct my vector X. We now say that a continuous frame does phase retrieval if you can reconstruct every vector from the absolute value of the frame coefficients. And one problem, though, is that if you take the absolute value of the frame coefficients, you can't distinguish X from negative X. And so we say it does phase retrieval if the only vectors we can't distinguish from the absolute value of the frame coefficients are the vectors X and negative X. Okay, so phase retrieval is something that has received a lot of attention and is a really interesting problem. But in applications, knowing that you can do phase retrieval isn't enough. If you actually want to do phase retrieval, you care about the stability bound as well. And so the idea of that is if you have two vectors, f and g and h, if you know the absolute value of their frame coefficients are close together, so if the absolute value of the frame coefficients of f is very close to the absolute value of the frame coefficients of g, then f has to be close to g, or f has to be close to negative g. And so that's the idea of stable phase retrieval, is that inverting the absolute value of the frame operator is Lipschitz, is the idea. Okay. So there's a lot of nice results on constructing good frames which do stable phase retrieval. And so in particular, there's some uniform constant, so that if you pick m vectors independently with either uniform distribution in the sphere or Gaussian distribution, and you choose a number of vectors on the order of the dimension of your space, then with high probability, your resulting frame does k-stable phase retrieval. And so the idea is picking random vectors can be thought of as sampling a continuous frame over a probability space. And so if your continuous frame, it has uniform distribution in the sphere, or it has Gaussian distribution, then random sampling gives you a frame which does k-stable phase retrieval with high probability. And this paper extends this result to lots of different sub-Gaussian distributions as well. So what we've done is prove that sampling a continuous frame to do stable phase retrieval requires actually discretizing the L2 norm and the L1 norm. And so the idea is, suppose you have a continuous Parseval frame of your Hilbert space. Suppose it does k-stable phase retrieval, and suppose it has this bound on the norm. And so this is our necessary bound for sampling to get a frame. If I look at the analysis operator, then the L2 of the norm of the analysis operator is proportional to the L1. And so being able to do stable phase retrieval requires the L1 and the L2 norm of your frame coefficients to be proportional. So if we think about discretizing a continuous frame is the same as discretizing the L2 norm on the range of the analysis operator, what we have is that sampling a continuous frame to get a frame which does stable phase retrieval involves simultaneously discretizing the L2 norm on the range of your analysis operator in L2, as well as discretizing the L1 norm of the range of your analysis operator in L1. And so even though what I was talking about before with discretizing norms on subspaces of LP, these Banach space ideas have applications in Hilbert space as well, which is pretty cool. One thing to point out with these results here, so all of these distributions are sub-Gaussian. one of the key properties about subgaussian distributions is there's very strong concentration inequalities. And with high probability, if you sample a subgaussian distribution if you have a continuous frame, which is subgaussian distributed, then with high probability, sampling it gives you a frame. And also with high probability, sampling a subgaussian distribution preserves the L1 norm as of your frame coefficients as well. And so this theorem about this relationship between the L1 and the L2 norm, every subgaussian distribution satisfies this. Okay, and I have just a few minutes left, and so I'm going to give a quick sketch of the proof of the idea. So suppose that you had a subspace where I take X, or suppose I look at the range of my analysis operator, and there's some vector in it with the L2 norm of the vector is 1. Sorry, the L2 norm of the frame operator of the vector is 1. And the L1 norm of the frame operator applied to this vector is very small. Okay, so we're assuming that our theorem is wrong. So let's draw a picture of what's going on. So we're in a probability space, so we can think about that as interval 0, 1. And the graph of a vector with L2 norm 1 and very small L1 norm is going to be very peaky. It's going to look something like this. So this is the L1 norm is going to be much, much smaller than the L2 norm. And then now the idea is that if I have a vector which is extremely peaky, and I have a bound, I have this necessary bound on the L2 norm of my continuous frame vectors, I'm going to have to find there exists some vector which is small on this subset here where theta of x is big. So this graph is big on this domain here and it's small everywhere else. I can find a vector which is small there and big somewhere else. And so this will be my vector. Let's call this theta of y. And so the idea is that if I look at the absolute value of theta of x plus y, this is going to be very similar to the absolute value of theta x minus y. Because if I add these two vectors together and take their absolute value, that graph's going to look very similar if I take this vector and then subtract this one and then do the absolute value. It'll look just like that. And so what we have is that if I look at the L2 norm of this, this is small. But if I look at the minimum of, or if I look at the norm of x plus y minus x minus y, this is 2 times the norm of y, which is 1. And if I flipped it, this is 2 times the norm of x. I'm sorry, 2 times the norm of y is 2, which is 2. And so what we have is that if it's possible to construct a vector with very small L1 norm, then I can pick a vectors x plus y and x minus y so that the absolute value of their frame coefficients is extremely close, but those vectors x plus y minus x minus y, this has distance 2, and x plus y plus x minus y has distance 2. And so the stability bound is bad. And so this is basically the idea of the proof. Okay. And let's see, the last thing I wanted to say was happy birthday, Dad. I hope you're watching this. It's your birthday tomorrow. So wanted to say happy birthday. And thanks everybody for listening to my talk.
All right, thanks, Dan. Everybody hit that react button. And Dustin, you can stop the recording.